Okay. So, now remember that when we write out Lewis structures, this is the method your book says. I took you through my method, right? Which is to count out your number of electrons, right? Take the thing that needs the most bonds, the most electrons, the furthest from a noble, put it in the middle, okay? Attach everything that needs to attach to it with a single bond around it, okay? Then you're going to fill in those things around it with full noble-like configurations. Then the thing in the center until you use up all your electrons, okay? And then you're going to move lone pairs from the stuff around it onto the center until you filled up everything to its octet or noble-like configuration, okay? Now I'll create your double and triple bonds. Notice my method has 2 extra steps to it, but that's because my method, you can never actually get wrong. If you follow my method, you'll always be right, okay? This method, you can most definitely get wrong. And then have to erase the whole thing and restart. Okay, so let's talk about naming covalent compounds. The binary compounds usually be composed of only 2 elements. They're going to be named with a 3-step procedure. You take the first element in your formula. Then you're going to take and just put that. There you go. The second element in the formula, you're going to change the ending to "ide." You're then going to designate the number of each element present using a Greek prefix. So, again, indicating the number of each element present is going to be important because nonmetals can actually combine with each other in a lot of different ways because they share electrons. They don't take the electrons from one to the other. Okay? And so you can have many, many, many different combinations, creating quite a complex variety. For example, we have here H2O, that's water, right? This is somewhat of an exception to the rule because their traditional names are so ubiquitous that even though there is an official naming method for it, people don't use it. Okay, they just use water, right? H2O. Ammonia is another example. That's NH3. Nitrous oxide is N2O. They should be doing a di here for 2. They don't. They just say nitrous instead. Okay, if you were actually to name them according to the rules I just presented, water would actually be dinitrogen monoxide. Okay? I have a little fun game that students in my classes have a tendency to play, and it is talk about water. Okay? Okay. So I have a compound. I kind of gave the game away. So you don't tell people what you're talking about. You say, I have a compound. It's called dinitrogen monoxide. This compound kills more people than every other drug and compound in the world combined.
Why is it nitrogen, not hydrogen?
Oh, did I say
You
nitrogen?
keep saying nitrogen.
Okay, because I'm looking at here.
Okay.
Dihydrogen monoxide.
Okay.
Yeah. It's a Freudian slip, I guess.
Okay.
Yeah. Probably because I was actually looking right here.
Probably.
Yeah. Okay. And so I have dihydrogen monoxide. And so it kills more people than every other drug and compound in the world combined. It does more property damage than any other cause. In fact, the next 5 different causes combined together do less property damage than dihydrogen monoxide. It is 100% addictive. Anybody that has tasted it or had it and put in them can never ever stop taking it. They will die without it. People have caused more wars over this compound, this drug, than every other cause ever to be documented. Yeah. Was any of that not true? No, it's all true, right? Yeah. And then dihydrogen monoxide is water, right? If you do this, the classes that have done this, and like students do this every now and then, even if I don't tell them to, even if I warn them not to. Last time they did it on Facebook, and they like did this joke as a Facebook post, and people were like, "Why is this like not outlawed?" It's on the internet. You can just click on it, and it'll go to the internet search, right? Like literally highlight it, right click, it'll search it. It would have told you. But people were actually like trying to do a petition to get it banned. And one person was, they were like joking back and forth and adding to it, like, you can add more things. I stopped. Um, and what people, his mother got so angry at this student because he was joking and having fun with it that she didn't talk to him for 2 weeks. No, the funniest part about this is that somebody did this joke back in like the late 70s before the internet to the Arizona state legislature. And the Arizona state legislator actually tried to ban water. Like, nothing against Arizona. You could probably do this to almost any state legislator. Most of them are so science inept that yeah, you can get away with a lot of things. In fact, Nintendo actually just patented the summoning of characters, which predates Nintendo's Pokemon by 30 years, if we're talking about video games, and by like 6,000 years, if we're talking about the concept. Just goes to show you how like incompetent the government can be sometimes. They actually gave the patent. Nintendo has a patent on that. I don't even know what to tell you. Like, wow. Nintendo was very clever with its phrasing, by the way. If you want to read into it, it's actually quite funny. Um, okay, anyways, these right here are the prefixes. They're Greek prefixes. Mono meaning like monocycle, one. Di meaning two. By the way, the bicycle is named for its two wheels, bi, two. Bi and di are interchangeable because there's arguments what the Greek is in English. Anyways. Tri, like tricycle, three, right? Tetra, like Tetris, four sides. Um, Penta, like the pentagon. Hexa, like hex wrench. And hepta, like the heptagon, of course. Okay. And by the way, we stop at 7 usually because nobody bothers naming anything after 7. So technically, you could go to octa and keep going on the Greek prefixes, on and on and on. But nobody bothers with it after 7. After 7, we have an entirely different naming method, and we'll talk about that further in the class. Okay. Okay. So, if we were to name this one, what would that be named as? Di, nitrogen, right? And then the oxygen here would be mon, and then it's oxide. You change the ending to ide. Okay? Let's try this one right here. So that'd be nitride right there. You'd actually put these in the beginning of it, by the way. That's why this is called ammonia usually. It's because they also write it backwards. Yeah. So it'd be tri-hydrogen, mononitride. Okay? Okay. So when we're talking about naming, you have to kind of go through this mental flow chart to name things. Are we talking about an ionic compound or a covalent compound? Okay. If we're ionic, then we need to look at the metal. If we're covalent, they're both going to be nonmetals, and so we need to name it covalent. Okay. If it's binary, it's going to be the methodology I just talked about with the Greek prefixes. I haven't taught you the other method if it's not binary. Okay. If it's more complex than that, because it's a whole series of rules. Because it gets pretty complex pretty quick. Okay. Okay. And so metals, these are they in group 1A, 2A, or 3A? If they're in groups 1, 2, or 3A, then they're going to be no Roman numerals. Okay? Don't need Roman numerals, don't need Greek prefixes. You just name them, the metal, and then whatever the anion is. Okay, and that will be things like magnesium oxide, right? Sodium oxide, sodium chloride. These right here, these would be, if they're not in these groups here, you're going to need the Roman numerals because you need to represent the variable charges, right? And so that's going to be things like iron 3 oxide. Okay. All right, so let's talk about moles. So first off, Mole Day is coming up. There'll be like a presenter and fun stuff, and usually the chemistry and biology departments do some kind of fun stuff on Mole Day. And that is 1023. And you'll see in just a bit why that is 1023, which is soon, right? Okay. Now, chemists, we use a unit. This is called the mole. We actually use this to relate the element in grams to the number of atoms it contains. The mole is going to be a unit for counting atoms. It's very similar, analogous to a package, like a dozen. Okay? So you get a dozen eggs, you get how many eggs? 12, right? You get a dozen sodas, you get how many sodas? 12, exactly. So anytime you hear a dozen, what does your brain say? 12. Yeah. And so I want that same relationship to develop in your brain for mole. When you hear mole, you hear package and a number. I'm going to give you the number in a second, but I want you to start developing that connection. Mole's a package of things. So mole, you could have a mole of pennies, you could have a mole of eggs, you could have a mole of dirt, you could have a mole of whatever. Okay? It's just that number of particles. Okay? You could have moles of atoms, moles of molecules, anything. Moles of pennies, you'd be very happy if you had a mole of penny. It's a big number. That's why I'm avoiding it for now. Okay. And so, again, when we talk about a mole, this is going to be a very strange looking number. And that's because you may have noticed that that periodic table did double service. Okay? When we looked at the periodic table before, we started with AMU, atomic mass units, right? And so a carbon weighs 12 atomic mass units, right? And then we started talking about as if it had some sort of relationship with grams at some point. And so when you look at a mole of carbon, it has a weight of 12 grams. Okay? And so mole is this very strange number that relates the individual atoms up into a larger quantity that's in grams. Okay? And so it ended up having to be a very strange number because they didn't know these things when they invented this. So, yeah. Life is difficult because of that. Okay, so again, if you have a mole of carbon, how much grams would you have? We look at the periodic table, and what's that number in the periodic table?
Atomic mass.
Atomic mass, yeah. So the atomic mass number is 12 point. Everybody? Okay, so let's call it 12 grams then, since you guys can't see it and not remember it. Okay, if we have a mole of hydrogen, what would be the mass of that in grams? You'd look up the periodic table again, you'd look up at that mass number, and you repeat that number, right? So 1.00075?
Probably
1.007.
So probably 75.
Yeah. And so that would be the number of grams for 1 mole of hydrogen. Okay? We look at nitrogen, and again, it would be that same sort of number. We just look at the periodic table, and that's the number of grams for a single mole. Can everybody make that connection okay? So if I ever asked you how many grams is a mole of this, you just look at the periodic table. All right. Now, this is called molar mass. That's actually what that number is on the periodic table. It's both the AMU number and the number that's molar mass. We've played a trick so we can have one number that has both those things. Okay? And we can have one number on the periodic table telling us these things. All right. Okay, so again, that is 1 mole of any element. This has a molar mass. That number is going to be in grams. It's usually represented unit-wise by grams per mole. Okay. Now the molar mass is going to tell us the mass of 1 mole of a substance corresponding to the mass of a single atom in AMU as well. It's the same number, but it is both units. Whichever units you need is the one you take. Now, let's talk about Avogadro's number and what exactly a mole is. Okay? So a mole is this number of atoms. It's a big number, right? Yeah. So this is it in scientific notation. And so it is 6.02 times 10 to the 23rd. Notice 1023 here. Yeah. So that's mole day. Because it's a mole. Yeah, I know. Technically, it'd be 6:02 on 1023 is mole time. But nobody's around at 6 p.m. at this university, so except for me, apparently. I seem to be the only one ever here. Everybody else runs away. All right. So this right here is going to be your scientific notation. This is referred to as Avogadro's number because Avogadro is one of the people that developed this number. And it is, again, the number of things that are in a mole. So if you have an Avogadro of pennies, if you have a mole of pennies, this is going to be 6.02 times 10 to the 23rd in pennies, right? Would you be happy with that? Yeah. It's more money than is on the planet, right? Okay. And so again, you can have atoms, molecules, particles, I don't care what it is, of moles, right? Okay, again, this is Avogadro's number. It's represented by N here, capital N. It's actually named in honor of Amadeo Avogadro. And again, it is this number here. Notice this is the equality for that number. So we have 6.02 times 10 to the 23rd atoms in this case. That would be 1 mole of atoms. Okay. All right, now this is actually a mole of carbon right here. It's still not a huge amount of carbon. I mean, keep in mind, it's only 12 grams of carbon, right? So in this 12 grams of carbon, there is 6.02 times 10 to the 23rd atoms of carbon. Okay? You guys have seen the weighing boats. That's actually not that big, is it? Yeah, it's actually pretty small. So it's just manageable amounts that you could actually weigh out in a lab. Basically, what it ended up being. All right, so again, it doesn't matter if it's eggs, bowling balls, atoms, molecules, ions, particles. If you hear mole, when you hear mole, what should you hear? A package of 6.02 times 10 to the 23rd atoms, or items, right? Okay, so this is the overall gist of how to do a calculation here. You'll notice it's the exact same thing as any other unit conversion, isn't it? Because we have an equality, we can set up a conversion factor, can't we? Okay. And so it's the exact same problem again. We just have this thing now. That's our new conversion factor. Notice it's just the equality set up with atoms on top. If you need to go the other way, you need to go 2 moles. What would you do to this? Just flip it.
Convert it.
Oh, yeah. So if you had 2
By
moles,
2.
you just multiply by this right here, right?
PO, not PW.
Okay. And so molar mass and formula weight. The formula weight for a compound is going to be the sum of the atomic masses. The molar mass of a compound is going to be numerically equal to the formula weight. The only difference here is the units. It'll have grams per mole, right? Because it's the number of grams for 1 mole of something. Now, to complicate the issue, biologists went and they just made a separate unit which has no difference from AMU whatsoever, is just AMU, and they called it Dalton. So they just named it for no reason. They came to it decades later and just like, Dalton, we renamed it. So That's biologists. They have to name everything. So you can make fun of those biologists. They rename the damn thing after somebody after it had been in place for literally decades before that person, like generations before them. So, anyways, Dalton, that is an AMU. If you ever hear about like DNA or proteins, they typically are measured in Daltons or DA or megadaltons, which is just the prefix, right? It's a million Daltons. And that's actually just AMU. Okay. And everything that's true about AMU is true about that. So if you wanted to take a mole of that, it would be in the grams that those atoms would be in. Okay. Okay. Now, let's talk a bit more about Lewis structures and covalent bonding. This right here is the tetrahedral structure. Okay. It's what happens when you have 4 domains around a center. It's going to make essentially a camera tristand. Everybody's used to the camera stands, right? They have the base of 3 things with one pointing up. Can everybody see the camera stand? Camera would be up here. Okay. The reason it looks like a camera stand is camera stands want the biggest base possible with the highest distance possible, right? So maximum separation. And that's what electrons want. They're repelled by each other, right? And so if you took 4 balloons and tied the stems together, you'd get the exact same thing. Okay? This angle, by the way, is 109.5 degrees. And again, this is referred to as tetrahedral. That's that shape. Okay, so let's look at how we can write this in 2-dimensional space. So we're going to use is what's called wedges and dashes. Right, this is how you can write in a 2-dimensional paper a 3-dimensional structure. And so what we're seeing here is the flat line represents bonds that are in the plane of the paper. Okay, they're just flat. The wedge here is coming out towards you. So that hydrogen is actually coming out towards you and trying to hit you right now. Okay? This one here, which is the dash, that's going away from you. Okay? That one's pointing back away. It's fading away in the distance, right? Whereas the wedge is jutting out and getting darker because it's coming towards you, right? It's bold. It's standing out towards you. Okay. Anybody have any questions there? Okay. All right. So the things that we are talking about, these are actually going to be where we have bonded pairs of electrons. They're going to repel each other equally. This is actually the reasoning behind these different shapes we're going to talk about. And this is what's referred to as VSEPR, or valence shell electron pair repulsion model. Okay? Essentially what it says is the sets of electrons are going to repel each other, and so they're going to spread out as much as they can. Okay? And that same reasoning is what I gave you for this one here, where we had tetrahedral because they're going to repel each other. They're going to try to be as far apart as they can get. Okay. Oops, weird. All right, so let's figure out how to determine the shape of something. What you want to do is you first want to identify the number of charge clouds or electron domains around something. That's what I've been referring to before. And so the number of electron domains are going to be areas that you have electrons in. Your book refers to them as charge clouds. I think that's actually a terrible terminology. It's kind of a dumb terminology, actually, because first off, they're electron clouds already, so it didn't make any sense. But anyways, I call them electron domains because it is the areas the electrons occupy and have dominion over or control over. Okay? And so you don't have, if you have 2 different kingdoms and the domains overlap, what happens? They fight, yeah, and then they push each other away, don't they? Okay? Same thing happens with electrons, right? Domains overlap, they're going to fight, push each other away. Okay? Okay, now, when you're talking about these charge clouds or electron domains, we need to talk about bonding and non-bonding. So bonding clouds or domains are going to be represented by usually a capital B for bonding, and these are going to be ones that are contained within a bond. Okay? And so, for example, we have the double, triple, and single bonds. Those are bonding domains. Non-bonding, they're lone pairs typically. So that would be like the one electron lone pair we have over there. And or the lone pairs we've seen on all these other ones, right? Those are going to be non-bonding domains. The big important thing about that is they don't have a atom on the other side. Okay? Think about it like this. If you had two people carrying a desk, would you be okay walking beside that? Sure, because it's not going to swing much, right? And so it's pretty safe to walk beside. Okay? What happens if you have one person trying to carry a desk by the end? Would you feel safe walking beside that when they're swinging everywhere? No, it's going to swing everywhere, right? And so that's like a non-bonding domain. Those electrons are not contained between two things. And so they take up a lot more space. Okay? All right. So this right here is going to be the Vesper and how we actually do this. This is where we get the different names for these things. So this right here is if we have 4 bonding domains. This is going to be tetrahedral for the molecular geometry. So let me again state that there's a difference between the electron geometry and the molecular geometry, okay? So the molecular geometry is going to be where we have the atoms at the end. So these are going to be bonding domains only. The electron geometry is just the geometry of the electron, period. It counts bonding, non-bonding, doesn't matter, okay? Okay, so this one here, this is tetrahedral both in the electron geometry and the molecular geometry. Everybody okay with that so far? 4 things around it. In this case, they're all bonding, so they're same. Electron and molecular geometry. Tetrahedral. This one right here, this is going to have 4 electron groups around it, right? 3 bonding, 1 non-bonding. And that's that lone pair. Okay? The electron geometry around this nitrogen in this case, that is going to be tetrahedral for the electron geometry. If we're talking about the molecular geometry, that is going to be trigonal pyramidal. See how it looks like a little pyramid here? Right there. If we just look at the atoms. And then it's trigonal pyramidal because it has a triangular base. So trigonal pyramidal, literally pyramid with a triangle at the bottom. Okay? Okay, and again, this is because the electron geometry is going to be 4 things that would be tetrahedral. The molecular geometry is the 3 bonding domains, and that's going to have a shape that is trigonal pyramidal. Mm-hmm. Yeah, it's front and back, 1 page of notes total. Mm-hmm. No problem. Okay, this right here is again going to be 4 electron domains around it, 2 bonding, 2 non-bonding, right? Okay. Now again, if we look at the electron geometry, it is tetrahedral, right? Same as the previous. If we look at the molecular geometry, this is going to be bent. Okay? See how it just looks like a bent stick? Okay. Now this one is going to have 3 bonding domains. Can everybody see it okay? That's our double bond right there. Okay. Okay, and so the electron geometry, trigonal planar. What is the molecular geometry then? Still trigonal planar, right? Because they're all bonding. Okay, this has 2 bonding domains only. And so this one right here is going to be linear. If you have 2 or 1 bonding domain, it's always linear. You can't not be linear. You only have 2. Because it's just straight. So let's go ahead and look at carbon and the different possibilities it typically falls in. So here we have 4 bonds around it. That's always going to be tetrahedral. If we have 2 single bonds and then we have a double bond, that's always going to end up being trigonal planar. And if we have two double bonds or triple bond, that always ends up being linear. All right, so again, non-bonded electrons, non-bonded pairs of electrons are going to take up space, but when you're talking about the molecular shape, they're going to be invisible. So while they do take up space, they change the structure. They're not going to be counted as part of the molecule. Okay. The non-bonded pairs of electrons are going to force bonded pairs closer together. You'll actually see it squeezes all the other bonds in that shape because they take up a lot more space. Bonded electrons are going to be confined between two atoms. Non-bonded are not restricted, so they're going to be able to fill out and take up that extra space. So right here we see an example where we have one lone pair, and you can see that the bond angle here is 107. This is in comparison to 109.5 when it was all bonded domains. Okay, and you see that it's actually squeezed these other angles and made them smaller. All right, because again, this takes up that extra space because it doesn't have anything to contain them. Okay, this one here has two lone pairs, and what we can see is that angle has been squeezed a bit more, hasn't it? And so it's 104.5 now. It's a little bit smaller. Okay, so this is the molecular shape of larger molecules. Realistically speaking, you can just take this Vesper theory that we had talked about and just go one after another. And that's why I was stressing the point that centered around X, right? I kept saying centered around this. So this is centered around this carbon here. We have a tetrahedral shape. This carbon here has a tetrahedral shape around it. This right here, which is the oxygen, is going to have a bent shape. Okay? And so if you wanted to know what this molecule looks like, you just add these together. What it ends up looking like is a bit like a zigzag. Like that. Okay? And that's why the line edge formulas, whenever we're writing those out, are zigzag. Okay, so let's talk about electronegativity. This is one of the few places where a chemist tried to have some fun and have a joke. Okay, so be prepared for a chemist's joke. Okay, so the electronegativity, this is the ability of an atom to attract bonding electrons of a covalent bond to itself. So this is when you make a bond, how much are you going to pull on those electrons and attract those to your end. Okay. So the element with the greatest electronegativity on the periodic table is going to be fluorine because the nobles don't make bonds, right? So if you don't make bonds, you can't attract electrons in a bond, can you? Yeah. So they don't have numbers for the nobles, at least most of the noble gases. The ones on the bottom, actually, they do have numbers, but they're pretty rare to use and you'll never use them. The electronegativity is going to increase as you move closer to fluorine. Especially on the top row, as you move over to the right, you have the smallest differences. As you go down, you're going to have larger differences. Okay? So, for example, oxygen has the second highest electronegativity. Chlorine and nitrogen have the same electronegativity. Okay? This right here is the numbers. So, fluorine has a 4.0, or F has a 4.0. This is the joke. Do you get it? So when you have a grading scale, when you have 4.0, what do you usually have for a grade? An A. And so a chemist was doing this, and he went, well, when are you ever going to get a 4.0 for having an F? Here we go. So it's the only place in the world where you get a 4.0 for having an F, right? Yeah, yeah. The funniest thing is he messed up the measurement slightly because, that happens. And so it's actually now a 3.98, which actually makes it a bit funnier, right? Didn't even get quite a 4.0, did he? Okay, now this right here shows you how they drop off. Again, oxygen is going to be the second highest. Nitrogen and chlorine will be the third highest. Okay, as you go down the period, you get larger changes. As you go this way, you get smaller changes. as you go further and further from fluorine, you have lesser and lesser changes because you don't have as much difference you can do. Okay? When we get down here to the metals, what do you notice about their electronegativities? They're really low, aren't they? What do metals do when they try to bond to nonmetals? Nonmetals take the electrons, don't they? Why is that? The electronegativity. There's a huge difference between the nonmetals and the metals, isn't there? And so when these try to bond together, the nonmetals just take the electrons because they have way higher electronegativity. Okay? When the nonmetals bond each other, the difference isn't so great, is it? And so they end up sharing the electrons, don't they? Because neither one can actually pull it away from the other. Right? Okay, so the inequality is going to occur when two different atoms are involved in your covalent bond. The electrons are going to be shared unequally when it's two different atoms. When two identical atoms share electrons, they'll form a fully covalent bond that they're shared equally in. Okay? The covalent bond in which the electrons are not shared equally, this is called a polar covalent bond because it has two poles. It has a positive and a negative end. And again, the one with the greater electronegativity is going to be the one that's negative because it's going to pull the electrons towards it. Okay. When electrons are shared equally, the bond is a nonpolar covalent bond, meaning it does not have poles that are positive and negative. It's equal charge on both sides. Okay, so uneven sharing of electrons in a polar covalent bond, this can be noted with several symbols. One of the most important symbols is the lowercase delta. That's this symbol here. It looks like a D. Okay. You may have seen this symbol other places. It actually means a partial difference. Okay. In this case, we have a partial difference because the electrons are being shared, but not equally. If you have a whole difference, that would actually be the uppercase delta, by the way, which is the triangle looking one. That's uppercase delta. Okay. So this right here is how you would write that. So here we have hydrogen and chlorine. They have different electronegativities. They're different atoms. And so you can see here that the hydrogen is going to hold on to the electrons very little. The chlorine is going to hold on to a lot more of that electron density. Okay? And what's going to happen is you'll develop a partial positive charge on the hydrogen, partial negative charge on the chlorine, because the electrons spend more time around chlorine, less time around hydrogen. Okay? Okay, and see the deltas here? Small lowercase delta positive, lowercase delta negative. Okay? This is the other symbol for that pole, right? So for the polar covalent bond, we put a plus, a positive side, on this side with the hydrogen, and then we're going to put an arrow towards where the electrons tend to move. Okay? And that's the other way you represent the dipole there. Now remember, this is bond dipoles, right? This is the dipole of a bond. Okay? If we have more bonds, we can have more bond dipoles. Okay. This right here is a covalent bond where they're shared equally, i.e. a non-polar covalent bond. And see, they're shared equally, so you don't have any charge at the ends. It's just negative around it, period, because there's electrons. Okay? Positive in the little centers, because that's where the protons are, right? Okay, so again, these bonds are going to be polar when we have these partial negative and partial positive charge. That means they have a positive end and a negative end, as in poles of a magnet, right? So if we're non-polar, sharing equally, we have no ends that are positive and negative. It's not going to be like a magnet, is it? All right. We can predict these using the electronegativities. It's the difference in electronegativities that cause these things. So if we have zero electronegativity difference between the two atoms, it's completely nonpolar. There's no end that's positive or negative. Okay? Okay, typically we call these nonpolar up until there's a difference of 0.4 between them. Because up to 0.4, there's so little difference that it doesn't really matter. Okay? And so we typically call those nonpolar covalent bonds. Once it gets to 0.4 up to before 1.8, those are considered polar covalent bonds. We'll have two ends. One is charged, one is negative, one is positive. And those are polar covalent bonds. Okay? Okay, once it hits 1.8 and on, It can get up to 3.3 is usually where you would see something. So 1.8 and higher, these are going to be ionic, meaning one just takes the electron from the other, period. They don't share them at all. Okay? Everybody okay with that so far? Okay, am I losing anybody there? No? Fantastic. Okay, so elements with an electronegativity difference of 1.8, these are going to transfer, that's ionic. Ones that have less than 1.8, they share, and that's going to be covalent bonding, whether it's nonpolar or polar. Okay? Again, the greater the difference in the electronegativity of the two elements, the more polar the bond would be, and the larger the poles on that bond would be. It's possible to distinguish ionic bonds from covalent bonds by looking at the types of elements present. Remember that the non-metals are going to have higher electronegativities. The metals have lower electronegativity. Overall, if you have a metal with a non-metal, it's going to be ionic, okay? Because the electronegativity difference is going to be large, isn't it? There are a few exceptions, but frankly speaking, you just don't need those, okay? There are some very interesting exceptions, though, if you ever want to talk to me about it. All right, so to distinguish between nonpolar bonds, the slightly polar bonds, and strong polar bonds, remember the facts. Fluorine is the most electronegative of all elements. The electronegativities increase as you move towards fluorine. Metals have lower electronegativity. Non-metals have higher electronegativity, which is just the same thing I just said right there, right? Okay, so the farther apart two nonmetals are on the periodic table, the greater the polarity of the bond between them. There is a major exception to this rule, which is hydrogen. So hydrogen, if you noticed on the table before, is like a 2.1 electronegativity. It should actually be close to carbon, about where boron is, essentially. Okay. And so hydrogen is a weird exception because of its period. It only has two things on, right? So it ends up looking like it's further, but it's not. Okay. And so carbon and hydrogen are typically considered nonpolar covalent bonds because their electronegativities aren't really that different. Right? You do have a slight difference in charge, but very small. It's not going to accomplish anything. Molecular polarity. Molecules can be polar or nonpolar. So remember, this is going to be molecules now. We were talking about bonds before. Now we're molecules. So this is multiple bonds together. A polar molecule is going to have an uneven distribution of electrons over the molecule. So we'll have a overall charge on the molecule that is positive and negative. Okay. A nonpolar molecule is going to have a more or less even distribution of electrons around the entire molecule, meaning it has no overall poles, no overall positive and negative end. So it's not overall magnetic. For the molecules containing only two atoms connected by covalent bonds, the polarity of the molecule is literally just the polarity of the bond. You don't have to worry about anything else if it's just two atoms. If it's more than two atoms, i.e. three and more, then you have to worry about whether they match each other or they oppose each other. Okay? And I'll show you an example in just a second. So the shape of the molecule becomes important. So this right here is carbon dioxide, and this one's water. Okay? Now, both of these have polar bonds. Okay? These are both covalent polar bonds on both sides of these. Okay, that's why we have these little deltas. Everybody good with that so far? Okay. Now, in the case of water, the shape is bent. And so what we see here is that they overall add together to give you an overall poles, negative on the oxygen side, positive on the hydrogen side. Okay? Can everybody see how those would add together? They're pushing the same direction, aren't they? A little of it cancels, but overall they're pushing the same direction. This right here, this is linear. So they're pulling the exact opposite direction, the exact same amount, aren't they? That means they're going to cancel out. You're not going to have any overall pull for this molecule. So the overall molecule of carbon dioxide is nonpolar. Okay? Again, the terminology, the molecular dipole, there is no molecular dipole for carbon dioxide. The molecule of carbon dioxide is nonpolar. Okay. The carbon-oxygen bond is polar covalent. Okay. The bond has poles, right? Not the molecule. Okay. Here, the molecule is polar. Okay. So water has a polar molecule. The molecule has dipoles, 2 poles. This right here, the bond, is also polar. Okay. Okay. This is how you represent the molecular dipole, by the way. See how they're canceling each other out in this direction right here? And they add together like so, right? And so you have an overall positive end this side, down here. You have an overall negative end on this side, which is the oxygen side. Can everybody kind of see that? If you had people trying to like pull a tractor, that's how that would work, isn't it? Okay. Okay. So this is your overall study guide for this chapter. And we have covered all the material. We're going to go back to that question now. And we're going to try to figure it out, right? Okay. So you have a sample of 32 grams of CH4. How many molecules are going to be in that? I know I'm making you use that mole, that Avogadro number. Oh my goodness. Avogadro, you and your number. Okay. Remember, this is just a straight up dimensional analysis unit conversion problem, like all the other ones were. Again, you just use what do you have, what do you need, and then how do I get them? I'm going to start erasing things. I'll collect answers, then we'll answer together. And if another people got it wrong, I'll go back and let you read. But don't try to get it wrong, because if it's like if I ever go, oh, you guys should have got that right, I'll just get it. Make a real solid attempt at this, because if you don't actually try it, you'll never know if you know it. And again, you could watch me do these things all day and not actually be able to do it yourself, right? That's why we have homework and we have clickers. Yeah. Okay, folks, I'll give you another minute or so. And then I'll take answers, and then we'll do it together. And what is next class period? Test. 1 hour long exam. It's 35 questions, by the way. Technically, it's actually a 40-minute exam, but some people will take the whole hours. Okay. All right, folks, get your answers ready. Hopefully some of these answers, when you saw them, you went, oh, that doesn't even make any sense. Okay, make sure you move your fingers around if it's not registering, and try to tilt it towards me. Very easy to block these with the fingers. Okay. All right, so let's go ahead and talk about this real quick, and I'll give you the answer. Okay, so I'm actually not going to give you the exact answer first. I'm going to let you re-answer after we do the work that you would need to use your cutler. Please don't forget to actually try doing these on your cutler you're going to use for the exam. You don't know how to use the cutler you're going to use for the exam, you'll get a bunch of questions wrong. Okay. Okay, now we have, what do we have? 32.0 grams of CH4, right? So I'm going to write CH4 here. Okay. I'm actually going to move that up. All right, so that is what we have. And what do we want? Well, we want the number of molecules of CH4, right? Okay. And so we see up here, I just taught you something called molar mass, which relates grams to moles, right? And moles are packages of things. So in this case, mole could be a package of molecules, right? Okay. And so what we need to do here is we need to go up to our periodic table and we need to go, okay, what is the molar mass of CH4? Okay. Well, there's one carbon, so we're going to take 12.0108 plus, and then we're going to go hydrogens, right? I'm just going to do one. There's 4 of those. Okay. And so I add those things together, and I'm going to get 16 grams for 1 mole of CH4. Can everybody see how I got that? Anybody get confused or lost? Please do let me know. Okay. Okay, so I think you all can kind of see where this is starting to go. All right, now, so we have this grams here, right? 32.0 grams. It doesn't have anything on the bottom because we don't have any equality. Okay. And then I'm going to take this. I want to get out of grams. So 16 grams is 1 mole of this, right? Okay, so now we're in moles. Not molecules yet. By the way, does anybody notice where this answer came from? Yeah. That would be if you stop here, right? This one, by the way, is up here. It's literally all the different numbers you get from this. Okay, now, hopefully everybody realizes pretty quickly, if you think about a mole, 1 mole equals how many molecules? Yeah, 6.02 times 10 to the 23rd, right? And so notice that automatically you're going to have a large number in these. Like you're either getting a very large number or a very small number. Okay? And so anything that's not a large number up there should make sense. Okay. And so I want to get out of moles. And so that's going to be on my bottom. My equality says the thing up on top has to be this right here, which is the molecule. And so I put that up on top. Okay. All right, so this is going to give me 2, which I then need to multiply that by. 2 times 6 is what? 12. And so this is going to be 12.0 times 10 to the 23rd. If I have an extra tens plate, what do? I can move it up in here, right? 2 times 10 to the 24th. If you want to redo your answer, please go ahead and re-scan in your answer. If anybody wants to try redoing that. Okay. Did anybody want to do some extra problems? I'm willing to work problems out if you want to take some time. I think I got it. Nobody wants to stick around if you want to do some problems. Otherwise, anyone that does want to do any problems or ask questions, take off. Have a good day. Don't forget exam.
What I do? Would you say it's more?
It is as even as I can get it.
Okay.
I can't give you like super